El Nino and La Nina are well known, and there are other oscillations which impact our weather more profoundly and are not known as well. We're going to go over three of them. These three oscillations impact surface pressures only. They do not have a synced-in movement with temperature. Now, I know that seems a little dichotomous because I've been training you that temperature impacts pressure. Let's see how this works for this. We're going to be talking about the Pacific Decadal Oscillation, the North Atlantic Oscillation, and the Arctic Oscillation. Let's go for it. The Pacific Decadal Oscillation is named this because it has a phase over decades, decadal. So this decadal oscillation has a cycle which goes about every 20 to 30 years. It's not exact. It is in the northern hemisphere only, and it only impacts winters. In a positive phase, you would have a weak Pacific high right here. And that weak Pacific high, remember, the high pressure pushes low pressure. When the high pressure system is weak, it has an impact on the low pressure, but the low pressure doesn't do the work on its own. Really, it's the high pressure either pushing or not pushing. So let's talk about that. This is a weak Pacific high in the positive phase for the Pacific Decadal Oscillation. And the weak Pacific high strengthens El Nino. Because remember, El Nino is the warming of the Pacific. El Nino represents less upwelling. Less upwelling happens with a weaker Pacific high to really bring down those currents and move them to the right, deflected by the Coriolis. So you have to get your head into the game that a positive Pacific Decadal is a weak Pacific high, is weak upwelling, is a warmer ocean heading toward the Western Pacific, is an El Nino condition. When we have a positive Decadal plus an El Nino, we have quite an amount of warming right off the bat going toward the Pacific that you can really see on infrared on satellites. In the negative phase, you can imagine that we might have more of a La Nina situation. And you would be right in that. So we would have, in the negative Pacific Decadal Oscillation, we would instead have stronger highs. Stronger highs bring more upwelling. More upwelling brings more cold water into the Southern Oscillation. It really takes down the surface temperatures. When you have a negative Pacific Decadal plus a La Nina, you've got very cool water heading through the Western Pacific into Indonesia. Really profoundly impacts their climate. So that is the negative phase for the Pacific Decadal that can be combined with the La Nina and produce one whopper of a climate change in those years. This is a great slide for the Pacific Decadal. It goes all the way from the 1860s, recording ocean temperatures up through the current day. So we have an enormous amount of data on this Pacific Decadal, and what you're seeing here are temperatures in Celsius and their differences in ocean water over those years. You can see here that these oscillations, these flips back and forth and pendulum swings happen over a decade or more for positives and negatives. So these are longer oscillations, but they are not exact. And the positive increases in temperature are associated with positive Pacific Decadal oscillations and are associated with El Nino warming of the ocean water, El Nino Southern Oscillation warming. And the negative Pacific Decadal oscillation is associated with cooling of the ocean water and the Southern Oscillation that is trending more toward La Nina. I hope this helps you to understand this a bit more and how these two oscillations produce swings, and these oscillations do not always work in sync. So you can see how climate change can get muddled in between these two oscillations, and the fact that the public doesn't understand these other oscillations that impact La Nina and El Nino. They just have heard of El Nino and La Nina. They haven't even heard of the others. So you will be ahead of the game for that. Another oscillation that impacts us quite a bit, and that really teams up with a third oscillation. The North Atlantic Oscillation teams up with the Arctic Oscillation, which conversely also is impacted by the El Nino. So you can see how these all impact our global circulatory system. In the positive phase of the North Atlantic Oscillation, you will have a strong Bermuda high here. And remember, high pressure pushes. High pressure pushes onto low pressure. And in forming this strong high pressure area over the Azores, it really impacts the pressure gradient force horizontally. And therefore, when it impacts those, you get stronger westerlies out of it that tend to move storms into Central Europe during those winters and tend to keep colder air masses up in the Arctic regions, leaving us with milder air masses. So this steering high, this blocking high, actually is blocking the cold air up into the Arctic. This is part of what happened in the winter of 2020, this past winter. We had a very mild winter, in part because there was such a strong Bermuda high that was keeping all of the cold air up in the Arctic area. There's some fascinating stuff that happened with ozone as a result of that, but we won't get into that right now. In the negative phase of the North Atlantic Oscillation, there is actually a weak Bermuda low. And you might say, that's not a Bermuda low, Bermuda's over here, and you'd be right. There's actually a weak Bermuda high. And you might say, this is not Bermuda. You're right, this is not Bermuda, this is the Azores. This high moves across the Atlantic back and forth with summer and winter. In the summer, it's known as a Bermuda high, and it's over here. In the winter, it moves over to the Azores, and it sits in the Azores for the winter. When this high is not strong, cold air can come down from the Arctic areas, and that usually means cold air impacts the United States. It weakens the horizontal pressure gradient force because this is not a strong high moving toward the low. It's not, so that this cold air can come down. It weakens the jet stream as well because you don't have those gradients and that drop in temperature that you usually would. So you may say this is not a temperature-based oscillation, it's more of a pressure-based oscillation. And I'm explaining it as a pressure-based oscillation, but you know there's always temperature involved somewhere. When we look at the pattern for the North Atlantic Oscillation, we don't have a neutral line in here at all. It's either positive or negative. And what you'll see is that this is a longer pattern as well. This can go for in upwards of a decade or more in the positive side. It can go in upwards of a decade or more on the negative side. It can also flip more rapidly than that. This is not a real predictable oscillation. That is why we didn't really see it coming this past winter. But it has been positive for the past few winters, then it slipped negative. This slide is a little bit low, and now it might be coming positive again. Its partner is the Arctic Oscillation, which really controls the air up above the Arctic Circle. When we have strong Bermuda highs, we can really keep that air shoved up above the Arctic Circle. That strengthens the pressure gradient force in the horizontal. That strengthens the Coriolis effect and the westerlies. That strengthens the jet stream. It keeps cold air in the Arctic. This happened this past winter. That was why we had such a mild winter down in the United States. We had a positive Arctic oscillation. Conversely, in the negative phase, we have a weaker high, which means that we've got less pressure gradient force. We've got less of a jet stream holding that Arctic air at bay. That means the Arctic air can come south and produce a colder winter for us. If we look at the work, we don't have nearly as much data on the Arctic oscillation. We've only have data from 1950s onward. The other was, 1860 was amazing. And we don't have neutrals here, really. We have a few neutrals. We have a couple neutrals in here, but not really a lot of data to go on. And you see that there are some long periods of positives. There are some moderate periods of negatives. And there is some up and down as well, particularly lately. This is not a real predictable oscillation, but it is one that we need to gain more information about in order to predict ice melting and Arctic ice flows. Hope this helps you out. We are on to Chapter 8. See you there.